So good morning and welcome back to the class on smart materials and structures. So before starting, can anyone let me know what we were dealing in the last class? Be quick. So Mo Nambal, you're there?
Yes, ma'am.
You just let me know what we dealt in the last class.
We studied about the control of structures, the
Okay,
modeling of the structures for control,
right. Then
then its limitations we studied, then equations we studied for.
before limitations, what we study. So we dealt about something related to controlling parameters, control and its strategies, if you remember.
Control parameters.
Yeah, control strategies we dealt about. After the modeling, we dealt about the control strategies. So then we went on related to the limitations which are available associated to our smart structures. Right?
Yes,
You remember?
yes, ma'am.
Yeah. So after that, I told that in today's class, we'll be dealing some actual smart structures which are already being developed and research which has been done related to the smart structures by using SMA actuators or PZT sensors and actuators. So I told that we'll be dealing with two cases to show the active structures which are there in practice. Right. So related to this, we'll be going first with systems using PZT sensors and actuators. So how and smart structure will be developed by using PZT sensors and actuators. And later we'll be going to see the structures which are developed by using shape memory alloy actuators. So you have studied what are PZT is nothing but a lead-based piezoelectric material, lead zirconium titanate based sensors and actuators. So it is of piezoelectric based sensors and actuators, wherein the first one is associated with shape memory alloy based actuators. How this type of devices are embedded in a system to be called as in smart structures. Right? So we need to know at least two cases. So it is usually with respect to the case studies, so wherein we see how the research work has been done exactly related to. So I'll be sharing the case study later to you in the Google Classroom as well. You can consider that to be as the case study for your third internals, right? So now I'm just giving you the just brief in touch related to the systems using PZT sensors and actuators. So first we are focusing on PZT sensors and actuators, right? So initially, before going into it, so there are various PZT sensors and actuators which are being developed. So it could be like for determining the energy harvesting. So this is for energy harvesting and similarly for pressure-based sensors. Okay, and this is an entire smart structure in which you have a sensor and actuator for acoustic applications. So we are clubbing how and device could be done based on different application. It is not like above the sea level only you'll be doing the smart structure. No, the smart structures could be developed for acoustic surface also. So wherein you can have a sensor, a actuator with respect to the acoustic surface. So the feedback usually will be assigned with respect to the controlling unit. So to term as a smart structure, you should be having all these three devices, what we have studied right from the beginning class, sensor, actuators, as well as the controller. So wherein you have these three devices together, you can term that to be as a smart system or a smart structure. So you can call it as a smart system for acoustic applications, and you can call that as a smart structure for any other structures what we do it above the sea level, right? So these are the system names what you have to understand to write, whether you have to tell a smart system or a smart structure, right? So this is mainly, so I just showed you related to the acoustic applications, and these are the other type of PZT sensors and actuators. But what are the basic things needed to perform for this type of devices? So that you have to know, right? So I told in every smart structure you can be having an control loops, which could be a closed loop or an open loop. So based on that also there'll be some bifurcation in the type of smart structure what we actually develop. So with this background, you can say that the first paper related to the smart structures was being illustrated by the person Finefield. Okay, so he was the first person in 1990s who gave an illustration how a smart structure could be implemented. So it could be implemented with various control schemes. That was the word what he put forward, so that you can get an structure beautifully arranged with respect to various other technologies. So here technologies comes into an picture, because you need to design an electric circuit. You should see like how the system is working, right, and which are the type of devices you are embedding together. So everything, a controller, electrical and electronic components plays a vital role, along with the material part. So material again comes with the composition of mechanical associated branch, and the other connection, the circuitry system, the open or closed loop system. It is a part of electrical and electronics. So it is like a mechano-electrical component which is embedded together to develop an complex system. So we need the use of upgrading technologies what we have to embed. So this person clarified and illustrated with proof that a smart structure could be developed or implemented by using various control schemes. So control schemes are nothing but the control strategies what I have explained you in the last class. And we need the use of other technologies also. So by using these things, he told that we can develop and implement a smart structure very easily. Okay, so based on that, he just showed an experimental approach how to perform a smart structure. So in his paper, he told that to perform a smart structure, he has developed a PVDF strain related sensors and actuators in a control room, right? So he told that to make a smart structure, these sensors and PZD based actuators. So both were used to measure the strain parameters. So embedding a sensor and an actuator to a structure with the help of a controlling unit will yield a smart structure. So in this paper, to develop a smart structure to identify the variation of the strain rate and the activities what to be performed, he told that minimum 2 control loops were needed. Okay, along with that, he told that we need to adapt an adaptive least mean square, which is in short called as an LMS. So this is being used to determine the harmonic component of the disturbance. So whenever you perform a work using a sensor or an actuator, there could be some noise or variation in the vent. So all these things will be sensed by the sensor. So there will be some disturbance along with the thing what you have to evaluate. So you need to have an adaptive least mean square thing to get the feed forwarded, so that it bifurcates all the harmonic components associated to the noise disturbance, or it could be related to the variation of the wave in the air which is coming in and out within a smart structure. So all the vibrations and the acoustic radiations which are disturbing the actual phenomena could be overcome. So he tells that, and hence it needs a one loop to see that the work is done properly, and other loop in order to eliminate the disturbances, so that the noise will not disturb the effective measurement of either strain, stress, your temperature, your pressure, your whatever for which you are using. So it again depends upon which type of sensors you're using, whether it is a pressure sensor, your strain rate measuring sensor, or to measure the temperature variations, or any other energy conversion phenomena, right? So when you evaluate these parameters, the noise should not affect the evaluation of this process, because the sensors are so sensible that they can even sense the noises and the disturbance, and hence this has to be omitted. And to omit, he told that we need to adapt least mean square method, so which takes the feedback of the disturbance which is coming, and that will fed to the another control loop. So the second control loop will take care of eliminating all the disturbances. So this was the thing which he concluded after performing the experiment. Okay, so here what he did is the structure, what he referred, had a thick walled aluminium cylinder. So he used a thick walled aluminium cylinder as a structure. So wherein this cylinder was bonded with PVDF strain rate sensors. So polyvinyl. So this is based on polyvinyl based strain sensors. So it was also an flexible piezoelectric film. Always PVDF will be flexible in comparison to piezoelectric. Piezoelectric is a ceramic material, PZT, so it will be brittle, whereas PVDF will be a flexible one. So the sensor what he used was PVDF based sensors, so which can measure the strain rate which has been induced in the aluminium cylinder. So based on the sensing, some instruction will be given by the controlling unit. So based on the instruction given by the controlling unit, these actuators, the PZD based actuators will perform the desired work. So this was the sketch what Mr. Finefield made to evaluate how a smart structure could be easily developed. Is this clear related to the basic thing how he formulated what are the prerequisites to develop a smart structure? Any doubt in this? Okay, so once you know about how to make a smart structure based on the required application, so then we can move further, right? So here, apart from that, in the cylinder, the vibration also can come into picture. So what he did is he used a conventional strain gauge and an accelerometer. Okay, so that these two instruments will help us to take the additional data. Additional data in the sense when you subject a load into the aluminium cylinder, then only the strain will be induced. So based on the strain, the stress will be developed, the body can deform or it can deform and re-come back to its original position based on the type of device it is. If it is not able to regain its original position, then it gets totally deformed, right? And also the cylinder could vibrate. So in order to evaluate the vibration modes of the cylinder, so this conventional strain gauge and accelerometer was used to take care of this additional data. And now a question might arise in you. So why the vibration component come into the aluminium cylinder, what we were discussing? Because the cylinder what we are using, which is made up of aluminium, will be driven by an electromechanical shaker. So you'll be having a cylinder, you know how a cylinder looks like. So if you connect that cylinder to an electromechanical shaker, so this makes the cylinder to vibrate. So due to vibration, there will be noise as well as different modes of frequency of vibrations. So to reduce this vibration, you should be having a vibration absorber so that the vibration comes down because it reduces the damping phenomena of it, or else you should be having something like strain measuring sensor which will be able to sense what is the strain induced due to the subjected load and the vibration. But this vibration, what is the frequency of the vibration you are getting? So to measure that, you should be having a particular instrument. So they used a conventional strain gauge and the acceleration with which it is vibrating. So you need to measure that quantity or the phenomena, and hence we need to have an accelerometer to it as well. So this was a thing what you have to keep in mind. Not only for a smart structure, if you have only a sensor, an actuator, and a controller that will work. No, apart from that, you should be able to embed the technologies which are essential, as he told in the beginning. Okay. So this is the thing what you have to understand. Yes. So this was connected to an electromechanical shaker by a single point contact to measure the vibrations. So once everything is set right, you have the smart structure connected with the required components. So what is our duty is to check the type of response you are getting, right? So from an available array of sensors, because I told you that you will be using the sensors to measure the strain rate. So you might be having an array of sensors which are bonded together, or an individual sensor to measure the strain rate depending upon what is the amount of strain induced. If it is a heavy load applied onto the device, that is a cylinder, so then you may need more than one sensor to measure the strain rate. If it is a mild and a feasible amount of load which has been applied, so then you may need like a single sensor, or else you may need an array of sensors. So you will check whether the available sensor is capable enough to measure the responses which are being received by our cylinder, which is connected to electromechanical shaker, right? So now once the sensor senses this is the strain range you are receiving, so you need some device which will perform a work. So that could be done only by active devices. So these active devices are nothing but our actuators. So here he used PZT based actuator, which is an lead zirconium titanate based actuator, directly telling it was an lead based piezoelectric actuator, right? So based on the data sensed, the actuator will be made to work. So to make these actuators to work, you should be having some control strategies which will provide you the set of instructions wherein the PZT actuator works. For that, you should be having a controlling unit. So based on the responses, the actuator will do the required work. So that will be taken only with the help of this integrated device. Integrated device is nothing but you should be having a controlling unit along with these two so that the work will go systematically. So this was the arrangement what he did to excel and see how one smart structure works by using PZT sensors and actuators. So in his paper, this fellow mainly focused on establishment of proper functioning of this particular instrumentation. He wanted to see how and the aluminium cylinder driven by an electromechanical shaker will work properly. So how the variations and the disturbance coming in it could be reduced by using strain sensors, right? So by using strain sensors, the strain rate could be analyzed and what is the result or the active work which has to be taken care. So that will be done by our actuators. So to evaluate his performance, he performed some sequence of experiments because after entire arrangement is done, you cannot orally tell that this was the achievement. Everyone will ask what is the proof. To show the proof, you need to perform some experiments and it cannot be satisfied with a single experiment. It is essential to do a huge lot of sequence of experiments. So to justify his concepts, so he did a sequence of experiments. So what was the experiments he performed? There is a huge lot of information in the case study. I am just briefing out entire thing so that the entire paper will be in your head. So any questions asked, you can answer. They won't ask you like in case study. It is a part of your syllabus where you need to show in practice how this PZT sensors and actuators are used in any smart structure. So please read carefully. You have two actual practices. Either of the one usually comes in the examination. So don't take it lightly. Be responsible. Listen in the class clearly so that you can write in your own words. Right? So this fellow Finfield evaluated the results by this sequence of experiments. So what are the experiments? You can see he has done nearly to 6 experiments, right? So what all experiments he has performed using PZT sensors and actuators in the smart structures. First, he has evaluated and verified the relationship between the sensor strain and the sensor rate signal, because we simply tell that the strain rate sensors are used to measure the strain, but how, in what rate you will get the strain rate? So when you can claim that is the minimum and the maximum strain rate, what is the relationship you get between the sensor strain and the strain rate signal? Because the sensor strain which has been sensed has to be converted into an readable data. So sensor strain signal will show you what is the rate of strain which has been induced in the device. So what is the relationship between the sensor strain and the strain rate signal? So that you have to come to know. Second one is using strain rate feedback to add damping to the structure. because when by seeing the strain rate, you'll come to know what is the amount of vibrations which are developed and how to reduce this vibration. To reduce the vibration, we should add some damping to the structure. So damping is nothing but the vibration absorbers. So based on the feedback you get, the strain rate feedback which has been mentioned here, you get only when you are using a closed loop phenomena. So when the smart structures are based on closed loop, then you will come to know the feedback of the strain rate which has been sensed by the sensor. So if the strain rate is very huge, that is a feedback. So then by default, you have to add a damper over there to reduce the amount of vibrations which are coming in. If the strain rate, what we are sensing is negligible or very less, so then it is like easygoing kind of thing, no need of adding the damping thing over there. So the strain rate feedback will help you to say whether a damping has to be added to a structure or not. For that, the sensor should work properly and it should yield the strain rates exactly, right? So based on the feedback, one will add the damping thing, whether it is needed or not. So damping here is nothing but the vibration absorbers, what we have studied already in the early part of our module 3, right? So all these experiments were connected in sequence one to other. So you should be very careful how systematically he has performed all the experiments, right? So after, based on the strain rate, he will think whether damping has to be added or not. So once this is done, what is the next thing is suppressing the vibrations with analog feedback control. I told you that the feedback will decide what is the rate of vibrations. If it is very huge vibration, then you should try to suppress the vibrations, right? So then the mode of vibration which has been performed by this electromechanical shaker has to be changed, fine-tuned, so that the vibrations comes down or you are suppressing the vibration. So this you can do only by getting the feedback, right? So this feedback will be from the strain rate. So once the vibrations has come to the range where the damping can be added, so then you can add. Abruptly, if you have a huge amount of noise, just by adding one damping effect over there, all noises will not be eliminated. At least if the vibrations what you're getting is within the range which has been acceptable, so then you can add a damper and reduce the vibration based on the feedback. So this feedback, what we are telling, could fine tune and get us the data only if it is associated to an controlling system. So here the controlling system plays a vital role. So you should be having the controlling strategies, what we have studied in the last class. You should plan properly and give proper controlling strategies so that it helps in getting a proper strain rate feedback, and then only you can reduce the vibrations, right? So this he concluded to us by his experiment. And also he did one more experiment, because orally if you see the data analog feedback control, you cannot store what is the data which has been got by the controlling unit. You should be having some digital way wherein you can store the data. And hence same thing, he performed another experiment to suppress the vibrations, but through a different channel. What was the channel? Can anyone let me know? It has been mentioned here also. Which was the alternate channel he opted for? Any guesses? Hello? It's been mentioned in the slide also. What is the next experiment he has performed? Sukrut?
Digital, ma'am.
Yeah. So the same thing he did by using a digital adaptive feed forward control, so that the feedback what he gets could be stored and that could be reviewed later. How we fine tuned, how we optimized so that the vibration was suppressed enough as per the requirement. Initially, he could not identify the digital one, so he did with the analog. So then he decided, okay, so since he did not get any data to be recorded, he told, let me check with the digital based feed forward control. So he was successful in this. And later, he performed one more experiment with a combination of two controls. So, what is this combination of two controls? He clapped both the analog feedback control as well as the digital adaptive feed forward control. So he compared in analog feedback control how we got the data and whether the data which was displayed was same as that of the digital recorded data or whether there was any variation in it. But successfully he was able to achieve almost the data were nearly mapping to each other. So he was successful in doing this experiment also. And later, finally, he thought how to reduce the acoustic emissions which comes out through the cylinder. Because whenever you use a cylinder and it is subjected to electromechanical shaker with the vibrations, obviously some amount of acoustic emission comes into the volume because it depends again what is the volume of the cylinder. So based on the volume, so what is the acoustic emissions which are associated with it? So thus it could be maximum depending upon the large cross-section area or it could be a negligible amount. So he tried how to reduce these acoustic emissions which comes out from the cylinder and he was successful from this. So one thing what you have to understand is when we are developing a smart structure, it is not an easy going work. There are so many things what you have to do as a groundwork. You should set the controlling strategies, the planning activities, which are the type of sensors and actuators you are using, and which are the type of controlling media you are using, whether you are offering a closed loop or an open loop system. So everything you have to think about and what are the other technologies which are needed to make your smart system work very smoothly. So to understand this and to conclude how one smart structure was, he has done more than 6 experiments here. So that shows the effort and the quality of the work what one has to assign if you need to have a good result out of it. So any work without effort will not give you a fruitful result. For namesake, you should never do it. If you study also, please study from your bottom of your heart. Then you will gain the knowledge. Listen to the class properly. So that will help you to keep the concepts in your mind. If that is the case, you can achieve anything in your life and you can write the entire paper in your examination in your own words. If you are not attentive in the class, then everything will be in wrong way. So you will just mug up and write something you might remember and something you might forget. So please take care, be responsible and study well. I hope these experiments, what I explained now, is it clear enough?
Yes, ma'am.
Yeah. So he performed these experiments. So this study successfully, when he did around 6 experiments, so this study demonstrated that a basic smart structure with the technologies such as PZT and PVDF sensors and actuators still need to be analyzed, means you need still an upgraded version of PVDF sensors and actuators if you want to develop a huge smart structure, because it was just a cylinder connected to the sensor, actuators and other technologies within a closed loop. For that, he did so much of experiments and concluded. But if you need to do this for a larger smart structure, the complexity gets increased. When the complexity gets increased, you need to have advanced versions of the sensors and the actuators which can function in a multiple way. And hence he told for this it was successful, but in future if you want to implement this for smart structures in a large scale, then it needs still advanced type of sensors and actuators wherein the complexity will be very much high. So to evaluate the performance, it is very much essential to upgrade the type of sensors which is being used. So this he concluded in 1990s, not now. So now still the many cases are happening. Why I took this is because you should know in actual what happened when it was implemented for the first time. So the details. what the Finfield gave was later taken by a person called Bruno Vicky in the year 1994, right? So he took the concepts of the Finfield related to the smart structure what he developed, basically a smart cylinder we can tell, right? So that concepts and the details were taken by Bruno Vicky in 1994. And later he presented his way of approach. So what he did is he presented the details of physical configuration of PZD patches on a structure. So what do you mean by PZD patches? I showed you a diagram here at the end. Yeah. So here if you see, right, you can see this is a cantilever beam. So at the cantilever beam, you have a mass. Usually the mass will be added either towards the tip of the cantilever or at the top, right? So when it has been subjected to vibration, it cannot provide you the required energy generation, right? It can just show you the modes of frequency of vibration. So that has to be sensed by using piezoelectric material. So here a layer of piezo material is being added. So if you have only one layer of piezo patch applied, it is called as an unimorph. If you have two layers of piezo patches applied, then we usually call it as a biomorph. So the same principle what Fenfield used in analyzing of the controlling system was analyzed by Brockville by using the piezo patches. So these piezo patches are called as unimorph or biomorph depending upon how many layers we have, right? I just came here to make you understand what you mean by unimorph and biomorph. So both are related to the patches. So what he did is he developed a model structure, and on the model structure he applied the PZT patches, piezoelectric patches. Again it was in lead based piezoelectric patches because in many decades before in 1990s only lead based piezoelectric materials were there. But now since last 10 years work has been started related to the lead free based piezoelectric, as lead based one are very toxic in nature. Okay, so he did the same work with respect to PZT patches. And he also told that while construction of the smart structure, we need two controllers, right? So one controller for required measurement and the other controller in order to omit the disturbances or the noise which is coming into the picture. So he also told the same things. So some of the findings, what he concluded is been mentioned over here. So what he told basically, so sensors and actuators what he used mainly consisted of PZT patches, wherein Finfield did not take PZT patches, he took the help of PZT patches, both in case of sensors and actuators. And these patches were bonded for a conical stub. So Fenfield used these PZT actuators and sensors which were bonded to a cylindrical unit, but wherein this fellow made the PZT patches bonded on a conical stub. So you know how a conical structure will be there. So he took a conical stub and on that the PZT patches were applied. Okay, so this conical stub was made by a graphite composite shell. So what was the material used for conical stub? It was graphite composite shell of 56 inches. So this was the material and its dimension what he used. And you need a length and tapering from a diameter of 3.5. So what is this? Because you need a cantilever. So on cantilever beam, you can apply the PZT patch. I showed you a diagram how a cantilever beam looks like. So this is a cantilever on which you need to apply a piezo patch. So what was the length of this cantilever beam? It's been mentioned over here. So the length and the tapering from a diameter was 3.5 inch. The tapered diameter was 3.5 inch and the length was around 1.8 inch. Okay, so this was mounted as a cantilever. So this one was considered to be as a cantilever. So on this cantilever, you had two sensor actuator patches. So you had two sensor patches and actuator patches. You cannot just keep these patches on the cantilever and go. When it vibrates, the actuator and the sensors will fall down. So what it has to be done, it has to be bonded properly to the opposite sides of the cantilever what you are using. So to bond, you should be having a proper adhesive what you apply so that the cantilever and the piezo patch will be bonded together so that when you have the vibrations of the cantilever, the piezo patch will be adhered to the surface and it won't fall down. So you should be using a proper bonding material. So they have given the dimensions for the actuator patch. The actuator patch was around 8 inch into 1.25 inch. So, and the sensor patch was 1.5 inch into 1 inch. So this was the dimension of the actuator patch and the sensor patch, what they used. And once the dimensions of the actuator patch and the sensor patch was ready, so these two sensors were placed 1 inch beyond the ends of the actuator. So if I just show the diagram here, this diagram is not of the case study what we are dealing. In the case study, there is no diagram as such. For your reference, I've just taken a diagram so that you can understand. So you can see that this is a cantilever beam and this will be the PZT actuator. Along with that, you'll be having a sensor patch which is applied here, one above and one below, right? Because it has to sense. So based on sensing, the work will be done by the PZT actuator. So the dimensions for the sensor patch as well as the actuator has been mentioned here and the location where it is being mounted. Okay. So this is about the location and the dimension of the actuators. So the patches what we add usually add some weight to it. So the weight of these patches were like approximately 5% of the weight of the structure. So it added 5% extra to the weight of the structure. Weight of the structure here is nothing but the cantilever. As thin the cantilever is, it can have that many number of free degrees of movement, right? So you can have different modes of frequencies. When the weight of the structure increases, the amount of modes of frequency also reduces, but it did not affect very badly because it added only 5% extra to the weight of the cantilever structure. So this was the arrangement what he did based on the PZT patches what he added up to the given cantilever. And apart from that, he used an analog controller, SISO based analog controller, to see what is the range of strain which has been induced, what is the strain rate. So based on the strain rate, what is the amount of vibrations that has to be absorbed. So for that purpose, he connected the cantilever. So when you have a cantilever here, so this is entire unit. So this cantilever has to be connected to the other electronic gadgets so that it will form a closed loop and it works systematically, because when the cantilever moves to and fro, vibration comes into picture. So when you have a vibration coming into picture, you should see what is the strain rate, whether vibration is too high or too low. If the strain rate is too high, first you have to fine tune the electromechanical shaker. So this is the electromechanical shaker on which the cantilever is being subjected. So due to this shaking, so you'll get more vibration in it, right? So if the vibration is very much high, then you should control the amount of electromechanical shaking which is coming in this media. So if it is reasonable enough, then you can add a damper and leave it so that the vibrations will reduce. And hence, to check all these, he needed an analog controller. So this analog controller usually consists of an Wheatstone bridge, and if you consider if you connect that to an oscilloscope, you can see what is the variation of the strain rate you are getting. scope will give you an oscillograph of the wave motion of the different modes of frequency. So by controlling the electromechanical force, the wave motion with reduced vibration can be observed, because when it vibrates initially it will be high and it comes down, showing that the damping has reduced due to adding of the damper here. So to understand the variations and to reduce the damping and to reduce the dampness, an analog controller was attached to the Wheatstone bridge, so which is nothing but our oscilloscope. Yes, we were here. Yeah. And also it consisted of a power amplifier. So power amplifier is needed because you need to connect the sensor and the actuator patches. So to make a connectivity between the sensor and the actuator patches, you need an amplifier unit. So amplifier unit, you can see here, an amplifier unit was there because it has to be driven by an electrical signal, or else how the electromechanical shaker will vibrate, right? So if you provide an input in the form of an electrical signal, then only the vibrator, then only the shaker can shake and you can get the required results in the form of vibration of the cantilever beam, and the required displacement will help you to evaluate what is the strain rate which has been induced. So based on the data of the analog controller, you can get the required variation in the strain rate. And hence you need an amplifier unit as shown in the diagram over here. So based on the amplifier unit, you can check what is the bandwidth of the damping nature you are getting. So that can be displayed in the oscilloscope here, right? So that you will usually get by a digital analog system. So that will help you to filter the unnecessary wave motions of the vibrations. So that could be achieved by a feedback loop. So every circuit system will be having a feedback loop. So that helps in knowing the variations. Okay, so this is the input what we are giving. So again from here you will get the output phenomena across the amplifier. So that will yield you the feedback. Okay, so based on that the vibrations could be controlled over here, right? So that is the thing which filters with the help of the feedback loop. So by using feedback control, a narrow bandwidth was achieved with required strain rate. So if you don't have a feedback loop over here, so unnecessary you'll be having high variations in the vibration, and you'll be adding more amount of dampers, means to say the vibration absorbers, to control the rate of strain rate. But if you have an automatic feedback controller here, you can directly reduce the vibrations and you can get the required strain rate data in the oscilloscope. So that is very much essential. This person also claimed the same thing. So this was possible by having a digital controller with 2 inputs and 2 outputs. So based on the input, you can see here again you have 2 inputs. So 2 inputs. So this is the input you are giving, 1 and 2. 2 inputs you have and 2 outputs you have. Okay. So this is called as a two-way digital controlling system. So this two-way digital controlling system helped to achieve the required frequency responses very well, and it was found to be within the range of 10 to 10k hertz, 10 to 10 kilohertz. So this was a range of the frequency responses what they were able to achieve by using the digital controlling unit. So this development helped to achieve the smart structures with respect to the actuator patches and the sensor patches. So they were easily able to construct a smart structure, not only a simple passive smart structure, it was an active smart structure. So you claim that as an active smart structure whenever you have an actuator in it. If you have only sensor to sense which has been happening, then it is a passive smart structure, because the sensors are only smart materials of the classification passive. You have studied in module 1 what is passive smart materials and what is active smart materials. And active smart material classifications are used to make active devices like actuators, wherein Passive smart materials are used to make only sensors which can sense, but it cannot take any action, and hence the name passive smart structures. Here, all the smart structures what we are dealing is related to active smart structures only. Okay, so you have to remember to use the word active smart structures. So this person was successfully able to construct an active smart structure based on the sensor and the actuator patches which were mounted on the given cantilever beam, and they had two digital controlling unit so that they could control the vibrations and get the required output of the strain rate in the oscilloscope. And to do all this, they needed an input data, so wherein they used amplifier as an input, so which provided two inputs and two outputs. And also the smart structure what he developed was most economical because it reduced the design effort, the fabrication cost, and testing requirements. It is in actual performance and seeing how it is working. So they did not need any modification in the design, and fabrication cost was very less, and there was no need to check the testing requirements. Once one demonstration done, so it is more than enough. In previous case, Finfield did around 6 experiments, if you remember. So the costing for 6 experiments would be comparatively higher. But he reduced the cost of the experiments also, because this single one shot of experiment was able to evaluate and check its performance. Overall, how the smart structure can work when you mount an PZT sensor patch and an actuator patch to the given structure. Here the given structure is nothing but the cantilever. Okay, so this is how he concluded finally. So this type of superior performance what he achieved was an much beneficial than that of the previous one which was developed by Finfield. So he told that it is like the performance of a control system could be tailored as per the requirement. So the type of the performance can be tailored in the sense a single structure can be used for more than one application. So if you have an active smart structure which has to be used for more than one application, then you have to fine tune the control system. So how you can fine tune the control system? By performing the customization to it, right? So you need to do the customization to the control system so that the performance of any complex structure could be obtained for different application purpose. So this was the thing what he achieved successfully. Was the experiment performed by Fenfield and Brovik both are clear to you all? Any doubts associated with this?
No, ma'am.
So if they ask you in the examination also, what is the best practice of smart structures you have observed using PZT sensors and actuator? You can tell about PZT sensor and actuator of Fenfield or related to patches, or you can compare how the actual PZT sensor and actuator performance was improved by using either Unimorph or Biomorph. Unimorph or Biomorph are nothing but the patches. If it is one layer patch in the cantilever, it is Unimorph. If you have two layers of the patch on the cantilever, it is an Biomorph, right? So these things you have to keep in mind, and if you know the concept, you can explain very beautifully. It is such a beautiful subject, you should just understand and write well in the examination. So once this case, the same case study will be there for your this one third internals as well. So this diagram I have explained you already related to the second part of PZT patches. So I don't think so I want to explain this again. So here there is one more diagram related to the pressure sensors. So what's happening here? So figure A shows the piezoelectric energy harvesting nano generators. So these are generators. So even nano generators made by smart materials are called as smart generators. If you want to explain anything related to smart generators, even that will be called as a smart structure. So what will be the structure of the smart generator? So you will be having a piezoelectric material here, and you will be having two patches. These are conductive substrates. So one will be having associated with positive charge, the other one will be associated with the negative charge. Because you can make it as a nano generator by adding an conductive layer, because piezoelectric material will be a dielectric element which is acting as an insulator. So to make a generator, you should be having a conductive element as well. So you'll be using a conductive layer as a substrate at the top and the bottom. But if you add both the case positive charges, when you connect, you cannot yield with the electrical power. So you should be having one coat of positive, another coat of negative charges. So when you apply a load in the form of an pressure or a sound wave or a force, the stress induced in the piezo material will help in converting into the electrical signal. So what is the amount of electrical signal that is being generated, so that you can come to know by blowing an bulb, right? So this generators helps in storing the electrical power, right? So if you have a smart road, and if what you call as a smart road, a normal road is not called as a smart structure. When you call a road as a smart road, if you have a piezoelectric patch beneath the road, right, and other connectivity with respect to technologies and the closed loop or open loop structure, so then you call that as a smart road. So if you have developed a smart road, and if you make the vehicles to move on it, so every vehicle will put huge amount of load on the smart road. So when huge amount of load is subjected at different points of the smart road, when you have a PZT layer below, so that load will be converted into the electrical signal. But that electrical signal which is being generated has to be used automatically. If it is not used, it gets wasted. But at that time, you cannot use automatically. Why? You need to have some generator associated with it. So if you have a generator, so then the amount of electrical power which is coming could be stored, or you can have a battery and LED batteries, and that batteries, sorry, lithium ion batteries you can use, and that batteries could be connected to the generator. So the amount of electrical power generated continuously from morning to evening could be stored in the batteries, and that power which is stored could be transferred where you need an application of electrical power. So these are the huge lot of actual practices what one has seen already as a smart structure by using PZT sensors and actuators as well. So there are many case studies what one can tell. So you can take any practical practice and explain also if you are interested into. So this is one more, the smart road, a smart structure through which you can explain, which helps in generation of the electrical power. So before going, I just wanted, this has been explained to you in the classes already, but still, so B is the resemblance of an piezoelectric material without an applied force. So here you haven't applied any forces, just you have different ionic moment, dipole orientation of the solid particles within the piezoelectric structure. After that, if you apply the piezoelectric effect, then all the ion dipoles turns in the direction in which the electric field has been applied. So then there will be a proper orientation across the dipole of the ions within the piezoelectric material. Right? So this is the thing which happens when the force has been applied in the direction. So then after the electric field has been removed, but still the polarity will be retained and there will be no much change in it. Means the amount of polarization achieved will be retained within the piezoelectric material, so that if you apply a load on it, the electrical power will be generated. Why I am telling you is, well, you cannot blindly make a piezoelectric material and keep here in between. You have to first prepare a piezoelectric material, synthesize and make a device. Once the device is on, you should make this device subjected to the electric field, so that the device what you have made will be polarized. So this polarized piezoelectric material then has to be coated at the top and the bottom for an conductive layer, positive and negative. So then it acts as a device in actual for use. So even though the load is removed, it won't go back to the original position. It will retain the polarization effect in it. So due to polarization effect in it, then only they can convert the load subjected here into the electrical signal. So these things are mandatory before you go into the device. And hence I'm showing you this. And this I have shown you already. So it is an acoustic surface application. So wherein you have a PZT sensor. Only one practice is needed. I've just shown you an other example only with the help of diagram. So for acoustic application also, below the water, you can have a sensor, a controller, and an actuator. Okay, so this will help you in developing the required external, internal, and reflected sounds in acoustic surface. How you can control the variation of the sound even in acoustic media. So that could be understandable easily by using a sensor. It will sense. So based on the sensor, it will send the information to the controller. What is the action to be made? So based on the instruction given, the actuator will perform the work and see that the required amount of sound light has been reflected within the area which has to be reflected. Okay, so this is an example for acoustic media. So this is done, and this is one more example of an smart structure which is used in health monitoring. Means suppose if you have bridges, right? So health monitoring of the bridges has to be checked continuously. Every bridge usually will be having a span of 100 to 150 years. So after that, the health condition of the bridges comes down, crack, fracturing, collapsing of the bridges. So if you have these smart aggregates embedded across n number of places, so that helps to check the health monitoring of the bridge until how many years the bridge can sustain or not. So this is also one of the example for the smart structures. So in this way, you should understand how in actual the smart structures are being developed. Hope the things are clear. Did you get any idea related to this?
Yes, ma'am.
Yeah. So now, Sukrut, what did you understand in today's class? What is the gist of usefulness of the smart structures? You please tell in your own words, nothing to tell from the things what I explained. You just tell what you have understood.
Ma'am, systems using the PSZ sensors and actuators. And the first paper was by the Finfield, and the second one by the Bronovicki.
Yeah.
And he took the, I mean, Bronovicki took the concept of the Finfield of smart materials, and
Yes.
he developed it was in the 1994.
Hmm.
And Finfield was, I mean, concept of the smart materials was developed in the 1990.
Hmm.
And he used the in the Finfield, he used the conventional strain gauges and actual, I mean, accelerometers to take the additional data on the vibration of cylinder. And
Right.
the vibration of cylinder were based on the electromechanical shaker.
Very good. Next.
And and
Okay. You told, what did you understand basically? So you, even if you need, you can develop a smart structure, right?
yes, ma'am, by
Yes.
conducting this experiment.
Yes, so they have shown you the flow, which are the things essential, which is necessary to see whether it is feasible or not to check and smart to perform a smart structure. If all those things are cleared enough, then you can go ahead with making a smart structure. Okay.
Yes, ma'am.
Yeah. So Dhanush.
Yes, ma'am.
Yeah. So what are the experiments Finfield did to evaluate a smart structure? Can you just name the experiments?
Yes, ma'am. Ma'am, verification of the relationship between the sensor strain and the strain rate signal, that one, ma'am.
Yes.
Then using strain rate feedback for to add the damping to the structure, ma'am.
Yes.
Then by reducing acoustic emissions from the cylinders, then using suppressing vibrations with combination of these two controls, ma'am.
Right.
Then suppressing vibration along the feedback using the feedback control, ma'am.
Okay. Good. Next, Srinidhi. Srinidhi. Srinidhi, you're there? Okay, I'll get back to him later. Sukrut?
Yes, ma'am.
Yeah, did you answer me? Okay. Mithun?
Yes, ma'am. Answer.
I think Srinidhi is there. Yeah, Srinidhi, if I ask you to make a smart structure, what is the thing which comes to your mind? What you might devise as a smart structure? If it is a simple one, also not a problem. What is coming into your mind? You just tell me. At the same time, everyone can type your name and USN in the chat room. Sukrut, do you need time? Sorry, Srinidhi, do you need time?
Yes, ma'am. I'm here, ma'am.
Yeah, I'll give you 2 minutes. Just think and let me know. By the time, Mohan number. Yeah.
Yes,
So how
ma'am.
did you feel about today's class? What is the importance of smart structures? Why there is a need of smart structures?
Ma'am,
Yes.
Who is going to answer me? Srinidhi or Mohan number?
ma'am, we studied today about the PZ sensor
Yes.
and actuators, ma'am. Like two concepts we studied about, which was done in
Yes, I
1980
know
and
that. I know that,
1994
Srinidhi. Just a
about
second.
the
What I asked you is, if I tell you to make a smart structure, what is the type of smart structure you think about making?
okay.
Please think and let me know. I'll ask the question to Mohan number. Mohan number.
Yes, ma'am.
Yes, ma'am.
Yeah. So now various structures are there outside. What is the need
Yeah.
in smart structure?
Because it gives better efficiency and feasibility of
Can
using this one.
can it be implemented in each and every structure?
Ma'am?
Can it be used in each and every application, or it has only specific thing where we can use as a smart structure?
It can be used in all the fields, I guess.
Yeah, basically we use a smart structure wherein the human beings are not able to identify. Suppose a bridge you have constructed, you cannot
Yeah.
wait and see until it gets collapsed.
Yes, ma'am.
You should be having something to monitor. It is called as a health monitoring of the devices what the human has made. So by seeing the health monitoring condition, you can come to know whether the structure what you have made is degrading or still in a good health. It is similar to that of human health. If you go to a doctor, he will use a stethoscope and check what is the condition of health of us, right? So by that check, he'll come to know what is the health condition of us. Similarly, we need to have some device which checks the health monitoring of the structures which are being done. So in that case, it is essential. Okay.
Yes, ma'am.
Yeah. Srinidhi, you can tell me now. Srinidhi, you're there. Yeah. Can you name at least one smart structure, what you have thought about?
Hello.
That I
Ma'am,
only
for
told, no?
health monitoring, ma'am.
Anything else?
That you
No,
told, ma'am.
you
For
should tell.
clinical.
Okay, anything else which comes to your mind, you can think and let me know. Harsha, you're there. Good morning. Harsha,
Yes, ma'am. Good morning,
how
ma'am.
are you?
Yeah, ma'am.
Yeah. So
Fine, ma'am.
can you just speak for 1 minute what you understood today?
Ma'am, it's some PJT. We are discussing about the PJT sensors and actuators, ma'am. It is an embedding structure to develop the smart structure and identify the variation of the strain rate. It is used to determine the harmonic components or type of the disturbance, ma'am.
Okay.
The acoustic radiation phenomena should overcome. The acoustic radiation phenomena should overcome and eliminate and use to eliminate the disturbance.
Okay. So be attentive in the class every day. So you'll be getting questions, or so you need to answer this. Okay. So now I'll take the attendance. Just 2 seconds. Yeah, you can mute your mic. Danush,
Yes, ma'am.
Mithun,
Yes, ma'am.
Mohanambar,
Yes, ma'am.
Sandesh,
Yes, ma'am.
Srinidhi, you were there. Where did you go? Sukrut, you answered me the question also. Kindly answer your attendance. Okay, and Arsha?
Yes, ma'am.
Yes. So I hope everyone have written your name and USN in the chat room. Yes. So please take care. Have a nice day. So we'll meet again tomorrow in the class. So until then, take care and bye-bye. Yeah. Bye-bye. Yeah.
Thank you,
Yes,
ma'am.
Thank you,
bye-bye.
ma'am.
Yeah, bye.